Hello friends, in this video I will discuss the crystal structure, which is basic step to understand the solid state physics and material science. And the topics covered in this video will be: first we will discuss the crystalline and amorphous materials, lattice, basis, Bravais lattice, unit cell, symmetry operation in crystals, and also we will understand the volume of a unit cell. So basically we know that matter can be classified in gas, liquids and solids. There are three states depending on their atomic arrangement. In the case of the gases, the atoms or molecules are very far, whereas in case of the solids, the atoms are very close. That's why solids are very dense materials. And in case of the liquids, it is the intermolecular or interatomic distance is in between the gas or solids. Solids can be classified in two classes, crystalline and amorphous material. So in crystalline materials, atoms are situated in a periodic array or in a regular manner over the large distances, whereas in case of the amorphous material, there is no periodic arrangement. So crystalline materials show long range order, whereas short range order is shown by amorphous material. The examples are like gold, silver, NaCl, ice. These are crystals, whereas in amorphous materials, the examples are liquids, glass, plastics, and crystalline material have a high melting point and they are hard, whereas in the case of amorphous material, they do not have any definite melting point. Why crystalline materials are so important? Because most of the material around us, they are crystalline, and the crystalline solids have the properties which depend on their crystal structure, how the atoms, ions or molecules are arranged in space, and it is easy to understand the behavior of the crystalline materials because the calculation are easier in the crystalline material, whereas in case of the non-crystalline material there is no orders, that why it is not easy to make the calculations or predictions. So why crystal structure is so important? We will see one example, the electrical resistivity of some carbon allotropes. And if we see the resistivity for graphite, diamond and fullerene, these all are carbon atom. So in case of graphite, it shows metallic behavior with resistivity versus temperature curve, whereas in case of the diamond, it shows insulating behavior, whereas this Buckminster fullerene or simply fullerene, which shows some superconducting nature. So these are just carbon atoms, but arranged in this different crystal structure. That's why their property changes drastically. So solid materials may be single crystal, polycrystal, or they may be amorphous or non-crystalline. Single crystal have the periodic arrangement or periodic structure across whole volume or up to very large distance, and every equivalent atom can be related with the other atom by translation or rotational symmetry. And we can see the single crystal have very uh, regular arrangement up to very large distances or even in the whole crystal. Here we can see a piece of a crystalline material, whereas it is very regular, whereas in case of amorphous solid, this structure is quite random. In the case of polycrystalline material, it is aggregate of many small single crystal, or sometimes it is known as crystallites or grains. And grains are separated by some grain boundaries, and the grains are usually in the range of 100 nanometer to 100 micrometers. And if the grain size is less than 100 nanometer, then these materials we call them nanocrystalline material. And polycrystals have some single crystal, means some order up to few atomic or molecular distances, and then uh, it it have some kind of change or in orientation, and that's why we have some kind of grain boundaries here. So different grains are here, and it is separated by other grain is separated by this grain by a grain boundary. In case of the amorphous materials, their ions, atoms or molecules, they are randomly oriented and they do not form the regular pattern. And they have this order only up to few atomic or molecular dimensions. It is also known as short range order. And the examples are amorphous silicon, plastics, glasses. And amorphous silicon can be used in the solar cells and also making thin film transistor in LCDs and displays. Crystallography is branch of science which deals with the geometrical description of crystals and their internal atomic arrangement. And symmetry of crystal is important because the properties, most of the physical or chemical properties, this depend on the symmetry of the crystal. We will discuss it in next class or next video. And structure should be classified into different type according to their symmetries, and then we can also make the calculation for the energy bands, which can tell about the electrical properties, optical properties, and different properties can be predicted using the energy bands, which can be calculated based on their crystal structure. So we will discuss the symmetry in next video. So let me understand the crystal structure. So crystal structure is basically defined as lattice plus basis. It is combination of these two. And what is lattice? It is an imaginary or hypothetical regular and periodic arrangement of points in space. And whereas basis is collection of atoms or molecules which can be fit on these lattice points. So here in this image we can see these black dots. These are the lattice points in space, and if we put some atoms or ions or any kind of shape, then it will follow uh, the crystal structure. So this is lattice plus some basis, and then we have finally a structure which is known as the crystal structure. And now we will discuss the translation vector, and mathematically we can understand it in this figure, that if we want to translate one point lattice point to another lattice point, then there is a vector like this n1a plus n2b. A and b are the primitive vectors, and n1 and n2 are the integers. Suppose we want to go from this point to this point, then we will have to add, suppose here a 1 2 3 4a plus 1 2 3b. So for in this image we can say that it is 3a plus 4b. So this will translate this point to here, which have the same environment as this point. So this is known as the translation vector. It is in 2 dimension. Similarly, in the 3 dimension we will have one another uh, case also, another primitive vector c also. So in 3 dimensional vector we can see that this r prime equal to r plus t. Here the translation vector is t, which is defined as ua plus ub bb plus wc, where u b w these are the integers and a b c are the primitive vectors in 3 dimension. So if we want to translate one point to another point, and if r is the position vector here, then r prime will be this r plus this translation vector. So it will change this point r to r prime with a similar environment as it have in the old location. And ABC are the primitive translation vectors or basis vector, and u, v, w are the integers. So this is the translation vector in 3 dimension. Now we will understand the unit cell, which is the smallest unit of crystal. It may be a group of atoms, ion or molecules, which reproduces the whole crystal on repetition. In two-dimension case, suppose we have a unit cell like this. So if we translate it up to long distance, then we will get the final structure. Similarly, in the case of three dimension, if this is the unit cell and if it is repeated several times, then we finally get the uh, whole crystal on repetition of this unit cell. And this unit cell, the unit cell may be primitive or non-primitive, which is also known as conventional. So in the case of primitive unit cell, there is only single point per cell, whereas in case of the non-primitive cell, there may be more than one lattice point per unit cell. And the primitive unit cell have the smallest volume, but it may not have the smallest volume. And the one example for the primitive unit cell is the simple cubic structure, where the atoms are only at the corner of the cell. And in this case, the conventional unit cell or the primitive cell is same, but in case of the BCC, we have some extra point at the uh, center of the body. So in the case of BCC structure, the conventional unit cell is not the primitive unit cell. So it is only in the case of simple cubic case. So how we can choose the primitive cell? Here in this figure, we have A, B, C, D, E, and F. There are different cells selected in this image, and we can see that A, B, and C, these are only primitive unit cell because atoms are only at the corners, so they are primitive cells. Whereas in D, E, F, we can see the atoms are also extra atom. uh, at the corners there are atoms, but there are also some atoms in the sides and in the center of the body. So D, E, and F are non-primitive because they have some extra lattice point. Now we discuss the parameters in unit cell, and the unit cell is determined by six lattice constants: A, B, C, alpha, beta, and gamma. A, B, C are the lattice vectors along X, Y, and Z axis, whereas alpha, beta, gamma are the angle. Uh, Alpha is between B and C, beta is angle between A and C, and gamma is the angle between A and B. And the crystal structure in three dimension have 7 crystal types and 14 Bravais lattices. So there are cubic, hexagonal, triclinic, monoclinic, orthorhombic, tetragonal, and trigonal. These are the 7 crystal system. So all the crystalline materials can be defined in this 7 crystal system. Now we will discuss the symmetry operation, which is important to understand the crystal structure. And symmetry, it defines the order, how the atoms are arranged and oriented in a crystal. And symmetry operators uh, will result that there should be no change to the order of atoms in the crystal structure. And combining these symmetry operator, it gives us point groups, which are the geometrically unique units, and crystal structure falls in some point group, and they are uh, they are defined in 7 crystal system according to their symmetries. So symmetries we will discuss in next lecture or in next video. We will discuss it in detail. So in the three dimension case, we have 7 crystal systems depending on their lattice parameters A, B, C, and alpha, beta, and gamma. There are 7 crystal systems which are defined as, for the cubic it is A equal to B equal to C, and alpha, beta, gamma are 90 degree. For tetragonal case, A equal to B does not equal to C, third size is not same, and alpha, beta, gamma are 90 degree. For the orthorhombic case, all sides are not equal, A does not equal to B does not equal to C, but angles are equal 90 degree. For hexagonal case, two sides are equal to B but does not equal to C. Two angles are 90 degree and one is 120 degree. In the case of monoclinic, all the sides are not equal. Two angles are 90 degree but third angle is not 120 degree. In triclinic case, which is the least symmetric, A does not equal to B, does not equal to C, and alpha, beta, gamma are not 90 degree. And trigonal case, all sides are equal, but angles are not 90 degree. So these are the 7 crystal systems, and Bravais gave some conditions for the unit cell, and then these 7 crystal classes are categorized in 14 Bravais lattices. Depending here, we have for the cubic, we have 3 kind of structure which are defined as P as primitive, I as body centered, F as face centered. So in the case of cubic, we have P, I, and F. So we have 3 classes. And in the case of orthorhombic case, we can see that P, I, and F, there is one extra lattice, that is side centered. Means some the atoms are at the corners, and also some atoms are at the sides also. So this is known as side centered. C is there. So for the orthorhombic case, we have 4 type of unit cell or Bravais lattices. In case of hexagonal, we have only one, trigonal one, monoclinic we have um, two less lattices, and in triclinic only one. So if we add these all, we will get 14 Bravais lattices, and these are the 7 crystal system, and these are the conditions for lattice parameter A, B, C, and angles alpha, beta, gamma. So cubic is highly symmetric because A equal to B equal to C, and alpha, beta, gamma is 90 degree, whereas triclinic is least symmetric because no sides and no angles are equal in this case. And the volume of unit cell is we can find out using the vector analysis that primitive shell is usually the volume of the parallelepiped, and from vector analysis we know that the volume of parallelepiped is the scalar triple product. If we have 3 primitive vectors A dot B cross C, and we will discuss in this video for the triclinic case because it is most unsymmetric, and if we get the volume for triclinic case, then we can get for the another cases also. So for triclinic, the volume is A, B, C, 1 minus cos square alpha minus 1 cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma to power 1 by 2. So how we can find out using the vector analysis, because A, B, C are the vectors of the unit cell, and the volume is V equal to magnitude of this A dot B cross C, and if we take the vector in component form along x, y, z axis in terms of unit vectors, A equal to AXI plus AYJ plus AZK, B equal to BXI plus BYJ plus BZK cap plus C equal to CXI cap plus CYJ cap plus C2K cap, and if we take the volume scalar triple product is and determinant form AX, AY, AZ, the component of this BX, BY, BZ, the component of C are CX, CY, CZ. So this is the volume, but we will take for some operations, we will take the B square to have the multiplication of these two determinants. So B square will be this multiplied by this AX, AY, AZ, BX, BY, BZ, CX, CY, CZ, this determinant multiplied by this. And now we can change in a determinant column to rows or rows to column. So if we change AX, AY, AZ as this, this row becomes first column, second row become second column, and third row become third column. And now we multiply. We know the how we can multiply the these determinants. So AX into AX, AY into AY, AZ into AZ. So finally we will get this kind of determinant, and then we have to use AX into AX plus AY into AY plus AZ into AZ, it will give us A square, and AX BX plus AY BY plus AZ BZ, that is dot product of two vectors A dot B, and similarly it is A dot C, and finally we have this kind of we can expand it A square. A dot B can be written as AB into cos and gamma, because gamma is the angle between A and B. In the case of A and C, the angle between A and C is beta, so that why A dot C we can write AC cos beta, magnitude of A, magnitude of C into angle between these two vectors, that is beta. So that's why we have expanded the dot product. And again we will have to expand this determinant. First we will have write a square, so b square c square minus b square c square cos alpha, similarly plus ab cos gamma, and if we expand it then uh, bc uh, a b c square cos alpha cos beta. So this is the expansion of this determinant, and finally if we take rearrange the terms a square b square c square as common, then we have in the bracket we will have 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. So finally we have the volume. If we take the under root of this, v equal to a b c and under root of this whole 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. So this is for the triclinic unit cell. So if we put different conditions for different unit cells, then we can find out the volume for different unit cell. Suppose for the cubic case, a equal to b equal to c and alpha equal to beta equal to gamma, then b equal to a into a, and cos 90 is 0. So that's why we will get a cube for the cubic unit cell. And putting these different parameters for cubic, tetragonal, orthorhombic, if we put a b c and alpha beta gamma for this general case, which was for the triclinic unit cell, and if we put these conditions, finally we will get for monoclinic case it is ABC sin beta, for orthorhombic ABC, cubic it is a cube, tetragonal a square c. So see these, using these parameters and angles we can find out the unit cell volume for different unit cells for different crystal systems. So thanks for watching this video, and if you have any queries or suggestions, please write in the comment box. So previous video was history of nanotechnology, introduction and history of nanotechnology, and next video we will discuss about the symmetry operation in crystal structure. So if you are new to this channel, so please subscribe. Thank you very much.